Okay, so this is the beginning of Chapter 3. I think you're going to love it. It definitely, sort of ties into Chapter 2 a lot, everything that we did. But the way you're going to get the answers for slopes of tangent lines and velocities and things that you already know how to find, the way you're going to get the answers is much, much different. So this section's title is Basic Differentiation Rules. And what I'm going to write is AKA derivative, maybe I won't, let's see, derivative shortcuts. Okay, so today in class, we looked at these three problems, and I asked you to find the derivatives using the definition for f prime of x, which is your limit as delta x approaches 0 or h approaches 0. What almost all of you came up with for this was the -7. For this one, you got -4 plus 6x, or actually I think you got 6x minus 4. And then for this problem, what did you have? 3x squared minus 3. And if you didn't get it right, I tried to help you fix it so that you could maybe come up with some kind of a pattern. Here are some more problems, and these ones are things that I said that you did from the last section, but actually I can tell the way these problem numbers look and the way the actual problems are is these problems came from the Larson calculus book. Now what you can do if you wanted to verify any of these is you can go through and use your f of a, as x approaches a, that definition would be pretty easy for most of these. And you could verify these different derivatives. I drew an arrow for this partially because I was out of room and partially because if you can think of a pattern, then you can finish this one off. Now, the derivative of 3 is 0, derivative of -5x is -5. The derivative of 3 plus 2/3 x is 2/3, which if you think about it kind of combines what we did here and here. This adds another sort of level to it. We have a 4x first. I know Ruth Ann kind of figured that out. I think Tristan kind of figured it out. How you're getting this. Lauren figured out that the power goes down. Let's see, over here, this is 3x squared minus 12. So let's come back to this one. You should at least know one of the terms for this derivative. Now, in derivatives like this, if you can rewrite the functions first, which is how you're going to have to do these, or the best way to do them anyway, think of 1 over x squared as x to the -2nd. Now, I didn't do anything to it. I just rewrote the function. So we're going to change x, or get the derivative of x to the -2nd, and it would work out to be this. Now, again, back when you were using the limit definition, you just would have left it alone. And if you can recall, you would have needed a common denominator in the numerator, and it probably took you about, I don't know, at least 10 minutes to do a problem like that. Similar with this one. You might have actually done this problem. If not, you did something, again, very similar to it. But if we rewrite this as 4x to the -1/2, then it's easier to recognize the pattern. So can you recognize the pattern? Give yourself, I don't know, pause this if you want to try and see if you can come up with the answer for number 20 before I write it. And spoiler alert, I'm going to write the answer in 3, 2, 1. Okay, so hopefully you gave yourself a chance to find it. 3x squared plus 2x. Okay, so how did you do? What happens? Well, anytime you have a plain number, a constant term, so here's a constant term, 3 is a constant term, -1 is a constant term, that is conspicuously absent in the derivative because the derivative of a constant is 0. Think about it. And we'll talk about this more in class tomorrow, but think about what a derivative is. It's a slope of a tangent line, right? If you have f of x equals 3, we have this horizontal line going through 3. What's its slope? Well, its slope here is 0. Its slope here is 0. Its slope here is 0. Its slope is a constant, 0. Okay, so its derivative is going to be 0. It should make sense. -5x. Negative 5x is just a line with a slope of negative 5. So what is its derivative? Its derivative is a constant, negative 5. So anytime you have a constant or a linear term, it's just 0 or it's the coefficient. Okay. Now when you have these other ones, a really kind of neat thing happens. This exponent comes down. If there's anything, see the 3 came down, 3, and the power gets decreased by 1. So the derivative of this is 3x squared. Because this is linear, we're just pulling off the 12. And it really does fit the power rule too. Again, we could talk about that tomorrow. But the 2 comes down, and since there's already a 2 here, it just gets multiplied by it, and then the power decreased by 1. This is a linear term, so we just pulled off the coefficient. This is a constant, so it's 0, and so on. Look, when we rewrote it, the negative 2 came down, so the derivative of this is negative 2x to the negative third. So that's what this is, rewritten with no negative exponents. The same thing happens here. Negative 1/2 times 4 gives you negative 2. So negative 2x to the 1 less powers to the negative 3/2, and then that got put down here. Okay, so definitely pause on this screen and write down all of your basic rules. We have 1, 2, 3, 4, 5 rules for differentiation here. Make your screen bigger if you need to. This just says that the derivative of a constant is 0. The derivative of x to the n is nx to the n minus 1. That's why the derivative of x to the third was 3x squared. That's even why the derivative of x to the first is 1, because it's 1x to the 0. So those linear terms actually fall into this rule as well. Here, this is why we just ended up multiplying the 2 that was already there up, as a coefficient, times the derivative of x squared. So it was 2 times 2x or 4x in that one problem. This says that the derivative of the sum of two monomials is the sum of the derivatives. And they don't have to be monomials, the sum of any two things. And same with the difference. And then the derivative of sine is cosine, and the derivative of cosine is sine. And I guess if I would have thought this out well, I should have had you graph the derivatives to discover that yourself, just like we did with the e to the x. Okay, now derivatives as rates have changed. Rate, as you have known for a long, long time, is distance over time. So an average velocity is the change in distance over the change in time. And you've done problems like that already. Or your average velocity, if the position function is written as s of x, or I'm sorry, of s of t, then your average velocity is the difference in y's over the difference in x, or change in position over change in time. And your instantaneous velocity is just your derivative of your position function, which now we have shortcuts for, so that'll be nice. And this is your basic position function. You can write this down for now, and we'll go over why this is a negative 16. Ooh, unless you can tell me, maybe I'll have that as an intro question tomorrow. If this is 1/2 g, that's 1/2 acceleration due to gravity, does one equation have a negative 16, and why does one equation have a negative 4.9? Yeah, that's what I want to look at. So try to be prepared to answer that question tomorrow when you come in. V sub 0, by the way, is initial velocity. So this is for free-falling objects. This equation is a position function for free-falling objects. This is disregarding wind resistance, air resistance, all kinds of different things. But say if you throw something up, you're on the ledge of a building, and you throw something up, and then it falls down. If you throw it up, its initial velocity is positive. If you throw something down off of the building, its initial velocity is going to be negative. And the height from which you throw it is your initial height, and that's your s sub 0. Okay, so if we just want to look at a couple examples. Again, I think you should pause this right here, try to find these derivatives on your own. Matter of fact, I'm going to pause while I write the answers for 4 and 8 and 10, so why don't you try 4, 8, and 10? And you know what? I don't remember. Now I can't go back. Did you write down the derivative of e to the x? Because I thought I remembered seeing it in the notes, and now I don't remember saying it, though. But we did it in class. Do you remember? We graphed e to the x And then we use the calculator to graph the derivative of e to the x. And do you remember it did the exact same thing. And Ruth Ann kind of saw it like that. She saw it in colors. Anybody with their color calculator? So anyway, the derivative of e to the x is e to the x. So I'm going to pause and write down the derivatives for 4 through 12. You should try to do them before you hit play again. Okay, so how did you do with these? Negative 40x to the 9th, 5e to the x, negative 3t to the negative 8/5. That's terrible. I couldn't read my own writing. Or negative 3 over t to the 8/5, although they started with a negative exponent, so technically you could leave it that way. And this one, number 12, you needed to rewrite it first, and then the derivative would be r prime of x, which was where you take your negative 7 down and multiply it by what's already there, times x to the negative 8th. And I just wrote that without negative exponents. All right, for the remainder of these problems, what you want to do first is you want to make sure that you don't have any products or powers or quotients before you start. Because if you notice on the last couple of pages, slides, frames, whatever, there were no formulas for those, and that's because they're actually a little more complicated. So this means I want to take x to the 1/2 times x to the first and make it x to the 3/2, and then minus x to the 1/2, right? I want to write radicals as rational exponents, and then I want to find y prime, I want to find y prime from there. So I'm going to let you do that. Same thing here. We want to turn this first into s squared over 4. For that matter, you might want to think of it as 1/4 s squared. Then we can find h prime of s. Come in with these, at the very least, blank in your notebook, okay? Because I'm going to reference this when you get to class tomorrow. This quotient doesn't have to be written as a quotient. You can take this up as an x to the negative first and distribute it through, or you can look at this as x squared over x minus 2 times the square root of x over x, which ends up giving you 2x to the negative 1/2. Then you can find your y prime from there. So this, and these last two I'm not going to write down, but you should. You want to rewrite this function as a e to the v plus b v to the negative first plus c v to the negative second, and then find its derivative. This is u to the 2/3 plus 2, I don't know why I said u, t to the 2/3 plus 2t to the 1/3 is how you want to rewrite that, and then you find the derivative. Okay, if you want to try to start the homework early, go to add line for the assignment because I don't have it as a final slide in here. And again, when you come over, or when you come into class tomorrow, I do want to go through the derivatives for 14 and 16, actually all the remaining problems on here, and see how you did. And then we'll talk a little bit more about, the rules and how you're putting them all together, and, give you some homework time tomorrow.